Now let's do some more practice problems regarding inclines and friction. In this case, two objects are connected together to form a system, not too much unlike the Atwood's machine. So imagine one block is resting on the incline and a string connected to it passes over a pulley, and hanging from the other end of the string is a slightly lesser amount of mass. So we'll say this one's got a mass of 3 kilograms, this one has a mass of 4 kilograms, and the incline is angled perhaps at 30 degrees. So first question, if there's no friction, what's the resulting acceleration of this system? It's hard to know for sure in what direction it's going to accelerate. So first of all, this is a larger amount of mass, so you might think that the acceleration points this way. But then again, that mass is not hanging vertically, it's only a component of the weight of the 4 kilogram object, so perhaps the system accelerates this way. Let's just start by identifying all the forces on the 4 kilogram object. So we're going to make a free body diagram as always, and I think I'll skip breaking mg into components, right? I just drew the normal force here on the free body diagram, so free of the object. mg would point straight down. That means it has a component this way and a component that way. No friction, so we don't need to worry about that, but there is some tension pulling in this direction. The question is that tension greater in magnitude than mg sine theta, and therefore the system accelerates in this direction, or is the tension less than mg sine theta, and therefore the system accelerates in that direction? Okay, so we're not sure, but we know whatever the case, the force pointing up the incline is tension. We've got to label this one mg cosine theta. Let's make a free body diagram for the 3 kilogram block. Again, we don't know how long to draw the tension vector, other than whatever length we draw the tension vector on this free body diagram is the same length we draw it on this one. But whether or not that's longer or shorter than the force of mg remains to be seen. Also, there's a problem here. In both cases, I just labeled it as m. I need to make a distinction. So one way we often do it is call one of them m1 and the other one m2. That's not bad. Another option, if you don't want to use subscripts, would be labeled the larger mass capital M and the smaller mass lowercase m. So let's do that. So I'll leave this as mg, but we'll change the label here to capital M. And all these little details matter in your problem solving. So spending more time setting up the problem than solving the problem is the key. And if you're cautious and thoughtful about your approach, it can help eliminate a lot of mistakes. Okay, so let's see. Well, 30 degrees makes the calculation somewhat easy. We know the sine of 30 degrees is 1/2, and we might as well just then calculate what would be this component of gravity. So this would be 4 times 9.8 times 1/2 give us 39.2 times 1/2, so just barely less than 20. This would be 19.6 newtons. Okay. Well, let's see. 3 times 9.8, what's that give us? 29.4 newtons. If we think of this as one complete object, just one system, then this tension becomes an internal force, and all we really need to do then is consider it like a tug of war. There's a force pulling on this end of the system to make it want to accelerate in that direction, and there's a force pulling in this direction on the whole system, make it want to accelerate this way. And clearly, 29.4 newtons is greater than 19.6, so at least we now know that the system would have a tendency to accelerate in that direction, and we can adjust the length of our vectors. It looks like I've got it wrong, and it's the tension that's greater in this diagram, and that means I have to draw the tension in this diagram just as long. Okay, but I also know it's accelerating downward, so this mg is drawn even longer than the tension vector. Getting a little messy. Tension points up, and the length of that vector is the same as the tension on that free body diagram, and then lowercase mg is even greater in magnitude. All right. Well, from these free body diagrams, now we can at least make a couple of equations. We can say that for the mass labeled as capital M, that the net force is equal to T minus mg sine theta. And notice I'm ignoring normal force and mg cosine theta because forces along the y-axis are sure to cancel out and create equilibrium in this case, at least equilibrium along the perpendicular axis. We replace net force with ma, in this case capital M. So ma is equal to T minus mg sine theta. Okay, from this free body diagram, it looks like the net force would be equal to mg minus T. We replace net force with ma. And if I take this expression, move it over here, I can add these two equations, and then the positive T and the negative T cancel out. There's going to be a common value of A that can be factored out. So A times little m plus big M is equal to, what are we left with? Little mg minus big mg sine theta. I guess I could factor the g out of that. So let's divide both sides of the equation by the total mass of the system and factor out the g. So we get an expression that says A equals g times the quantity lowercase m minus capital M sine theta, all divided by little m plus big M. We've done enough of these example problems now that you're probably starting to see a common theme. Whenever you have the original Atwood's machine, which is just two blocks hanging vertically, or you have one block on an incline and another one hanging over the edge, or maybe it's not an incline, one of them's on flat level and the other one hangs. It seems like we always get a result that the acceleration of the system is g times some expression that depends exclusively on the masses in the system. So if we call them M1 and M2 instead of lowercase and capital M, the question is, what exactly goes? Well, it depends from case 1 to case 2 to case 3, except it seems the denominator always comes out the same, doesn't it? Yeah, in every example we've done so far, the denominator has been nothing more than the sum of the two masses. Well, that's really because the acceleration of the whole system should be inversely proportional to the mass of the whole system, and we find the mass of the entire system just by adding the two individual masses together. Okay. So that's exactly what we have in this case. That's the result we got. I can tell you what the equation for acceleration would be for the simple Atwood's machine. It's A equals g times the quantity m2 minus m1 over m1 plus m2, assuming that m2 is the larger of the two masses. In this example, A equals G times, well, we know the denominator is going to be m1 plus m2. The numerator in this case is just m2 all by itself. And that's because the weight of block number 1 is canceled by the normal force, and there's no other force pulling back in the opposite direction. So the tension can be thought of as an internal force to the system, so the weight of block 2 is the only external force, so mass number 2 is really the only quantity that's tending to increase or drive the acceleration of the system. So if you think about a system like this one, then the acceleration should be g times the quantity. Well, the denominator is going to be nothing more than a statement of the total combined mass of the whole system. And if we see the tension as being internal, right, we made free body diagrams individually for each separate object, but that tension and that tension, when we view the object as a whole, becomes an internal force. So the external forces really were like this tug of war I was expressing. It's the difference between the full weight of the vertically hanging block and the component of the weight along the incline for the other block. In other words, the numerator in this equation is well, here I'm calling it lowercase m, capital M, but in this picture I'm calling it m2, m1. So this would be m2 minus, well, it's not just m2 minus m1, it's m2 minus m1 sine theta. It's only a component of the gravity that is opposing the forward motion up the incline. So with practice, you can eventually look at a situation, whether it's two blocks hanging vertically, one of them's on an incline or one of them's on flat ground, and without going through the process of making the free body diagrams, you might be able to just jump straight to the equation. But I don't recommend doing that until you've internalized that process more. At this point, it's probably best to take the time to make the free body diagrams, because in doing so, you will confront the concept behind the problem more. So I know I'm getting a bit off track, but as a side note, I would challenge you to see if you can come up with an expression for the acceleration of this system. Maybe this is angled at an angle we'll call alpha, and the other part of this ramp is angled at something we'll call beta, and we have a block capital M on the steeper incline. It's attached over a pulley by a string to a smaller mass we'll call lowercase m. And the question is, what's the equation that governs the acceleration of this system? So if you catch my hint, you know it's going to be in the form A equals G times some expression that only deals with the masses, and you'd probably guess that the denominator is nothing more than, well, I'm not going to say any more. See if you can figure out what this expression is. Why don't you take a guess at it and then go through the process of making free body diagrams for the individual blocks and see if you can actually prove that your guess is correct. But back to the problem at hand. I'm going to draw it again so we remember where we were at. Four kilograms, 3 kilograms, 30 degrees, and what's the acceleration? So we've derived A equals G times the quantity, we'll call this lowercase m, capital M. So times the quantity, lowercase m minus capital M, over the sum of the masses, m sine theta, right? It's only that component of the weight of this block that opposes the motion. So the acceleration is 9.8 meters per second squared times 3 minus 4 sine 30, all divided by 3 plus 4. Let's see, sine 30 is 1/2, 4 sine 30 then would be 2, 3 minus 2 is 1. The acceleration is 1/7 of 9.8, which comes out to 1.4 meters per second squared. Great. Well, that's just the first step of this problem. We make it more challenging by asking this question: what if the angle remains 30 degrees and we still have the same two blocks, 4 kilograms and 3 kilograms, but we say it's not frictionless, right? The force of friction is not equal to 0. In fact, what minimum coefficient of friction would be necessary to keep the system at rest? So now that we know the tendency without friction for this system is to go up the incline, then we know any force of friction is going to point the other direction in an attempt to hold it at rest. So that informs our free body diagram. So we make a free body diagram first for the 4 kilogram block. Normal force, tension, stick to the script and make that a capital M, capital MG sine theta. Oh, since that's just a component, it should be an open arrowhead. And mg cosine theta. So this doesn't look balanced, right? It looks like the tension is greater in magnitude, but if the friction force is non-zero and it points back this way, then it would be the sum of the friction force and the component of weight that's offset by the tension. Now the free body diagram for the 3 kilogram block is much easier. Now wait a minute, how come this time I drew these forces equal? Prior, they were definitely out of balance. The weight of the block was greater in magnitude than the tension. But then again, this was the case when we knew it was accelerating in this direction. Here, the nature of the problem is what's required to keep the whole system at rest. So the tendency without friction would be to accelerate this way, but it turns out the acceleration is 0, and that only happens if the net force is 0. And so we can say that the tension has to equal the weight of the 3 kilogram block, and just as well, the tension based on this free body diagram has to be equal to mg sine theta plus force of friction. So we can combine these equations together by substitution. Say mg, little mg, has to equal capital mg sine theta plus friction. Okay, so which type of friction? Kinetic or static? Well, definitely static. This is a problem about keeping it at rest. And static friction is not just strictly equal to the coefficient of static friction times normal force. Instead, frictional force can be as much as that value, and certainly greater than or equal to 0. But this is a limiting case problem. Once again, we're asked for the minimum coefficient of friction. So we're going to take the case where we have the force of friction is the maximum value. So we substitute for force of friction, the coefficient of static friction times normal force. Now wait a minute, we don't know what the normal force is, but our free body diagram suggests that forces in opposite directions have to be equal for the case of equilibrium. So in place of normal force, I can substitute mg cosine theta. So lowercase mg equals capital mg sine theta plus mu static times capital mg cosine theta. Now can I just divide both sides of the equation by m? There's an m in every term, but be careful, that m is not the same as these m's, so no, I can't cancel it out. We're trying to solve for mu, so do a little algebra. Mu static times capital mg cosine theta is equal to lowercase mg minus capital mg sine theta. Divide both sides by mg cosine theta, and we get a final algebraic result. The coefficient of static friction must be equal to m, lowercase m, over capital M cosine theta minus, you see what you get? When I divide capital MG sine theta by capital MG cosine theta, the M and G cancel out. I'm left with sine over cosine, which is tangent. So in this case, our coefficient of static friction has to at least be equal to 3 divided by 4 times the cosine of 30 degrees minus the tangent of 30 degrees. Grab a calculator and see what you get. Tangent of 30 is 0.577. And this part of the solution comes out to 0.866. And so our final answer says the coefficient of static friction has to be greater than or equal to 0.29. Now 0.29 what? What are the units? No, well that's a silly question. Remember, the coefficient of friction is a dimensionless quantity. Okay. Let's add one more wrinkle to this problem. Four-kilogram object, 30-degree incline, connected by a string. 3-kilogram object hangs vertically. And as long as the coefficient of static friction is greater than or equal to 0.29, the system remains at rest. So let's say it's greater than 0.29. Let's say the coefficient of static friction actually happens to be equal to 0.5. Then how much weight, how many additional weights can you start to stack on top of here? How much additional mass can be added to the 3-kilogram object and still have the system remain at rest? Well, I don't think the free body diagram changes at all from the previous example. If it remains at rest, then we still have tension pulling up, mg pulling down. The only difference is this m is no longer 3 kilograms. It's going to be some larger value. And the 4-kilogram object still remains at rest. So in the end, this equation we derived here would still apply to the case described where the coefficient of friction is not 0.29, but actually a greater value than that. Okay, so where did this equation come from? We can go back one more step in our work to here. Now this time we're just solving for a different quantity. Instead of algebraically isolating for mu static, now we want to use this to isolate for lowercase m. So we get mg, if you allow me to do the work here, would be equal to mu static times capital Mg cosine theta plus capital Mg sine theta. We can factor out the capital Mg. Let's move our work down to here. And we can divide everything through by g, right? Cancel that out. So lowercase m is equal to capital M times mu static cosine theta plus sine theta. So lowercase m equals 4 kilograms times 0.5 times the cosine of 30 degrees plus the sine of 30 degrees. Now we know that's 1/2. This is 0.433. So 4 kilograms multiplied by 0.933 gives us 3.732 kilogram. But remember, there was already 3 kilograms here, and the question was how much additional mass. So the additional mass would be 0.732 kilograms. Thanks for watching.